Hi, welcome back. In this video, we're going to finish a problem that was started in class. I'm going to start at the beginning and finish it, and then try to relate it to what we did in class today when we were talking about areas. So in this problem, we are given a table, and the table shows speedometer readings at 10-second intervals for a race car. So, for example, at time 0 seconds, the speedometer reading was 182 miles per hour. At exactly 10 seconds, the velocity was 168 miles per hour. So these aren't the velocities during the entire 10-second interval. They're just the velocities at specific times, like the instantaneous velocity. Like somebody took a picture of the speedometer at 10 seconds and it said 168 miles per hour. All right, so we're going to use this information to estimate the distance that the race car traveled during the 60-second period. So see, there's 6 time intervals, each of them 10 seconds long. So it was a 60-second race. So we're going to get the whole distance traveled during that 60-second race using the velocities at the beginning of the time intervals. So what that means is we're going to use the equation distance equals rate times time. Remember what that equation means. It means that if you're going at a constant rate r, for example, I'm driving at a constant rate of 50 miles per hour on the freeway, and I drive for, say, 2 hours. If I go at a constant rate of 50 miles per hour for 2 hours, that means I've traveled 100 miles during that time. But rarely do we go a constant speed, right? So that formula works only when you have a constant rate. So what we're going to do in this problem is use those 10-second intervals and use the speedometer readings at the very beginning of each interval to assume that the race car was going that fast for the entire 10 seconds. So for the first time interval, from 0 seconds to 10 seconds, we're going to assume the car was going 182 miles per hour on that entire interval. The second interval between 10 seconds and 20 seconds, we're going to use the speed 168 for the entire interval. The next one, 20 to 30, we're going to use the speed at the beginning of the interval, which is 106.6 miles per hour. And the interval from 30 to 40, we're going to use the velocity at the beginning of that interval, which was 99.8 miles per hour. The next interval from 40 to 50 seconds, the beginning of that time interval, the speedometer reading was 124.5. And then during the last 10 seconds, from 50 seconds to 60 seconds, we're going to assume that the race car was going 176.1 miles per hour that entire time. Even though that was just the reading at the beginning of the interval, we're going to use it for the entire interval. And so now we're going to use these mini rates and time intervals to get these mini distances and add them all together. But first we have to remember, so t is going to be the time interval, the length of the time interval. They're all 10 seconds, right? But we have to notice, oh, look, our speed is in miles per hour. Our time is in seconds, so we got to convert. So 10 seconds is, there are 60 seconds in a minute and 60 minutes in an hour. So 10 seconds times 1 hour for every 3,600 seconds gives us delta t is really 1 over 360 hours. All right. So now let's set up an approximation for the total distance traveled by the race car. So it's going to be the distance traveled in the first 10 seconds, which is approximately 182.9 miles per hour times 10 seconds, which is 1 over 360 hours, plus the second distance, which is 168 miles per hour times 10 seconds. The third distance would be 106.6 times 10 seconds. and then 99.8 times 10 seconds, but instead of 10 seconds, of course, I'm using hours, 1 over 360. The fifth time interval is 124.5 times 1 over 360. And then the last time interval, the distance was 176.1 times 1 over 360. And if I pull out the 1 over 360, using the distributive property, I can just add up all these rates and then multiply that sum by 1 over 360. So that's just using the distributive property, save myself a little bit of multiplication. After I add those numbers together, divide by 360, I got 2.4 miles. Total distance traveled in that 60-second race. So, how does this relate to what we did in class today when we were approximating areas and defining the definite integral? Well, we can look at what we just did, rate times time, graphically. So I'm going to use a different velocity function, right? So here I'm going to graph a constant velocity function. So the example I gave before when I said constant rate, when I said drive 50 miles per hour for 2 hours, that's a constant rate. What does that look like graphically? Well, a constant function is a horizontal line. So if I'm going a constant rate, then the graph of my velocity function is a horizontal line. So let's say we want the distance traveled between time t equals a and time t equals b. What do we have to do? Well, we're going to multiply rate times time. Distance equals rate times time. And the time is the time interval, delta t, which is just b minus a. And the rate is a constant rate, which is just some number, k. So, for example, 50. And what are we doing? Well, we're multiplying rate times time. Well, we're calculating the area of a rectangle. So that's the distance problem if we have a constant rate. We're just finding the area of a rectangle. But what if we don't have a constant rate, which is like real life? So say our velocity function looks something like that. It's not a constant. And we want to approximate the distance traveled from time A to time B using that velocity function. Well, what we can do is chop up the time interval. Let's say chop it up into 4 equal time intervals, subintervals. Could be 10 seconds long. Let's just call the time intervals delta t. They're all the same. There's 4 of them. All right, and now let's use the velocities at the beginnings of those time intervals like we did for the race car. So in this case, my delta t, I'm just going to write down is b minus a over 4. We don't really need to use that in this example, but it might look familiar because we saw something like that earlier today. So what I'm going to do is, in this example, just use the velocities at the beginnings of these time intervals. Well, those velocities are these y-coordinates of these points on the graph at the left endpoints of the subintervals. So, for example, I can draw a bunch of rectangles. And so I drew a red dot at the point on the curve where we're going to calculate the velocity or use that velocity. The height of each rectangle gives us the velocity at the beginning of each of those time intervals. So if I set up the approximation for the distance that I've traveled using this velocity function, it's going to be approximately the sum of 4 distances traveled on each of those time intervals, those subintervals. And they're all, the subintervals are all the same length, delta t. So it's going to be rate times time. So v1 times delta t, where here's v1, it's the height of the first rectangle, plus v2, the velocity at the beginning of the second time interval, times delta t, and v2 is the height of that rectangle, plus v3 times delta t. v3 is the height of the third rectangle, and the last velocity times delta t is the fourth distance traveled, and there's the last velocity. So what I'm actually doing is calculating 4 areas. I'm finding the areas of 4 approximating rectangles. They're all under the curve. So when I add those together, we're calling that L4. Remember, we used R4 and L4 today in class. L4 stands for 4 subintervals left endpoints. So that's what we're doing. We're approximating the distance traveled using 4 rectangles left endpoints, whose heights are calculated at the left endpoints. And we can see from the picture, this is an underestimate of the distance. So that's very, very much like what we did when we were approximating areas today. This is the same problem, approximating distances. You're finding the area, or approximating the area under a velocity curve. And if we wanted the actual distance, we'd have to take more and more and more rectangles, and we take the limit as the number of rectangles goes to infinity of the sum of all those distances. So we take finite sums of distances, d1 plus d2 plus d3 plus all the way up to dn, and then we'd take the limit of that sum as that number n goes to infinity, and that would actually be a definite integral. All right, so I hope this helps tie together distance problem with area problem, and you can see why a definite integral comes in handy. All right, watch for more videos, more handouts, and examples, and I will see you next time.